Let's look at more specifically at the details of the convection. Before that, we'll just remind ourselves of the MJOs that we saw in the first chapter, the classic figure from the seminal paper by Madden and Julian from the 1970s that has been reproduced by many other papers. This one from Daehyun Kim's paper. Showing the various phases of convection originating in the western Indian Ocean and then propagating eastward across the maritime continent. Here we are looking at that same structure in terms of the 850 hectopascal winds and OLR. As you remember, outgoing long wave radiation is an indicator of convection. When deep convection happens, cloud tops end up with cold temperatures and the OLR is reduced. So negative OLR in this case usually filtered and presented at intraseasonal time scales as a deviation from the mean. So negative values here correspond to convection and the positive values correspond to dry phase of the MJO. Sea level pressure is shown here. As you can see, under the convection there is convergence, raising of the moisture, and the clouds are shown as occupying the free troposphere, and then there is divergence and sinking over the high sea level pressure ahead, so that corresponds to these phases. We'll see soon that the MJO actually in general in the equatorial region convection produces two modes where sea level pressure is propagating much faster than the convection, even though there are indications of Kelvin wave like structures in the propagation of convection and OLR. So what is it that slows down the OLR convection propagation as opposed to sea level signature that propagates fast? I'll come down to various processes in the convection like dissipation, friction, and so on. Okay, so that's that. Let's moving on to the convection and large scale. This is the integrated heat transport as a function of latitude here. So it's the summer and winter latitudes which have been composited to produce the equatorial trough sitting in the summer hemisphere. It has zero integrated heat transport. It is known as the energy equator. We will not get into details right now, but essentially ocean is moving heat into the northern hemisphere and the atmosphere is moving back into the southern hemisphere. Especially in the winter hemisphere, you can see there is much larger heat transport in terms of 10 to the 15 joules per second, and there is lesser northward heat transport here. So you have a divergence around the equatorial trough, which is essentially our ITCZ, not saying whether we have averaged and so on. We're just looking at some ideal situation here and looking at meridional winds 10 degrees from the trough in the winter hemisphere. You have convergence into the ITCZ, and you have divergence above. So you can begin to see the link between the lower and the upper atmosphere, and how this happens is a key question. So that's what the chapter is all about. Okay, so obviously we have to start with the structure and where an air parcel can be raised. So we are showing here the potential temperature in the solid black line, and we have equivalent potential temperature here with its negative gradient and instability, and we have the saturated equivalent potential temperature. We already know that when you raise air parcel from the surface as a dry parcel, then there is no condensation heating, there is no buoyancy change. It is just the pressure effect. So this is stable. No matter how much you raise it in the atmosphere, you're not going to cause any instability. Okay, whereas in this side if you raise the parcel, for example, A to A prime, you can quickly saturate it because you go from this potential temperature, equivalent potential temperature to the saturated equivalent potential temperature here. And then the question is, how do you go above this? What gives you the buoyancy to go above this? That's one of the key questions we will try to answer. And this paper by Reel and Marcus, I hope I got the name right. Yeah, Reel and Marcus from the 1950s, 1958, argued that there is a ascent of the undilute plumes. Basically, that means once you accomplish this buoyancy, you can keep rising because you don't have mixing with the generally drier air around. So you are just able to rise to the point where the moisture has been condensed out and you reach the dry potential temperature, or the equivalent the potential temperature here. Okay. Whereas if you are rising here, you are going to rise to B prime before you hit saturation, and on this side you are basically not going to get saturated at all, even if you rise all the way beyond here, because you are not going to hit the saturated equivalent potential temperature. So any air parcel you lift to the left of this is not going to accomplish saturation. So reading this more carefully, for dry processes the atmosphere is absolutely stable. d theta dz is partial theta partial z is greater than 0. So no matter how far you raise the parcel, it's not going to get saturated. However, if moist processes are taken into account, the tropical atmosphere is potentially unstable to the mid-troposphere. So here, till about 500 to 600 hectopascal, you are unstable because you have this negative d theta e dz or d theta e star dz profile. Okay, so trajectory A to A prime shows that an initially unsaturated surface parcel can achieve saturation at position A prime if it is raised vertically about 100 to 150 hectopascal. We are not saying anything about exactly how we can raise it, how the work is done to raise it. Any parcel to the left of B, for example this C, will not reach saturation, as I already said, irrespective of the degree of lifting. So the left ordinate here in kilometers shows the amount of work against gravity necessary to raise a parcel and achieve saturation if is greater for columns to the left of A to A prime. So if you go beyond this, you need more energy because you are covering more height here to reach saturation. You are not going to reach saturation here at all, and so on. So A prime to E here is the hypothetical undilute ascent that I mentioned, because if you mix dry air, you are going to lose buoyancy and you cannot rise anymore, right? And you will sink back. So if you want to rise all the way to E and completely dry out the moisture and reach the potential temperature here, obviously at high altitudes there is no humidity, so air parcels do lose their humidity, but that cannot happen unless you have undilute ascent. Okay, then over time it became clear that there are no such undilute plumes to be observed. Okay, so Ed Zipser writes very well here. Recent decades of observations over tropical oceans from 1974 to the present in the tropical Atlantic, offshore of Taiwan, offshore of tropical Australia, and the warm pool of the equatorial Pacific have yielded data from aircraft penetrations of thousands of cumulonimbus clouds. Observations show great consistency. Undiluted updraft cores are not found. So this is the hypothetical undilute plume here, that they are just not found. Okay, He also summarizes further that so he argues that if above this level, oops, if the water that is saturated now can freeze and further release the latent heat of fusion, then you can again gain buoyancy and keep rising. But it turns out that that's not so easy, because the latent heat of fusion is very small to explain this ascent. The observations over tropical oceans can be hypothetically explained by assuming large dilution of updrafts by entrainment below the 500 hectopascal, that's the mid-troposphere, followed by freezing of condensate. So he says you don't need undilute plumes, because anyway they are not observed, but if you reach the mid-troposphere, then you are getting cold enough that you can release the latent heat of freezing. This freezing and subsequent ascent along an ice adiabat reinvigorates the updrafts and permits them to reach the tropical tropopause with the necessary high values of moist static energy, as the hot tower hypothesis requires. The hot towers are these deep convective plumes that reach all the way to the top of the atmosphere, as the observations show. So we're trying to explain the observations in terms of where the buoyancy would come from. Of course, this idea is not very solid, because if you look at the latent heat of evaporation and latent heat of fusion, the ratio is very small, which means the heat released from latent heat of fusion or freezing of the water into ice is not really that large. Okay, and yet we know that from these figures there are widely distributed cloud structures reaching to the top of the atmosphere, and there is convection associated with those towers. So basically we have to explain these observed structure in terms of how you would lift air parcel to the saturation level and then keep continuing to raise it all the way to the top of the atmosphere. Okay, that's what we will do with this cute diagram here in the next podcast.